Hello and welcome to Train Signal. This is wireless video number 2, wireless terminology. Here's our table of contents. In this video we'll learn why is wireless important? What's so great about wireless networking? Why should we care about wireless? We'll talk about radio frequency and different terms associated with that, gain, loss, how radio frequency works, how do we understand it and measure it. We'll do some RF math, radio frequency math, learn about terms like amps, volts, watts, milliwatts, decibels, and so forth. We'll learn about signals and how antennas work, different spread spectrum technology, 802.11 standards and organizations, types of wireless networks, and how authentication and association works on wireless networks. Now this video is mainly a theory video. We go through the theory of wireless networking, all the different terms and terminology that are important to every wireless network engineer and anyone who's taking the CWNA exam. That's the Certified Wireless Network Administrator exam. So all of this terminology is very important for that exam, but it's also important to anyone who wants to configure a wireless network. To really configure it properly and understand what's going on, you need to understand the different terms and how the wireless network really works behind the scenes. So with that, let's move on to our first topic. So why wireless? Why do we care? Why is wireless so important today when it wasn't that important yesterday? Well, the simple answer is that people move and networks don't. And what that means is with a regular wired network, like an Ethernet network, you can install that wired LAN all around the building and try to anticipate every place that you think people will have an office, every place they might work, put those jacks in a conference room, put them in the break room, everywhere. But invariably, those people will find some place to work where they don't have an Ethernet jack, and they'll ask for an Ethernet jack to be installed there. Or they'll move their desk on the other side of the room, and they'll want the Ethernet jack closer to their desk so the cable doesn't have to go around the edge of the room or whatever. They'll find some place where they'll need another Ethernet jack. So on a regular wired network, you have to have a cable technician come out, install the new jack, patch the cable over in the IDF, and get the new jack up and running. And all that takes time and it takes money. And it's inconvenient for both the user and the network administrator. So the great thing about a wireless network is that the network can move with them. Well, as a wireless engineer, the network really doesn't move with them, but the network's hopefully always there, no matter where they go, as long as you've installed an access point in that area to give them wireless coverage. Now, as network engineers, we also know that installing access points everywhere and giving wireless coverage everywhere is a lot harder than it sounds to most people. So another reason that wireless is important is that expectations have changed. Due to cellular phones, people today have cellular phones and they use those cellular phones everywhere, and they expect to have great signal strength no matter where they go, and they expect their cellular phone to work whether they're in a skyscraper or in a rural area or out on an island. They still expect their cellular phone to work. And those same expectations have been moved over to wireless networks. So no matter where people go, they expect to be able to pull out their laptop and use that laptop either on a wireless network at a hotspot or in a hotel or in a house or on a cellular network. They just expect that network to work. Also, today, life is faster paced, meaning people move around faster. They expect to be able to pull out their laptop and do their work quickly and get it done, and be able to use the network to do that. They also have this expectation that the network is everywhere. There's a popular ad campaign that, it's all in the network. So wherever they go, they expect to be able to use the network and get on the network. And that's why wireless has become so much more important today than ever in the past. Also, there's so many portable devices today. PDAs, the PDAs have cell phones in them and cameras and laptops, and they're all using wireless. So that's why we care so much about wireless, and that's why wireless is so important. But wireless, to be able to work properly, also has to be implemented properly and has to be done right. And it's difficult sometimes for people to understand that when they're able just to take out their home access point and plug it in and get on their little wireless network without any configuration. They expect to be able to do the same thing no matter where they go, and they expect the wireless engineer at their company to be able to do the same thing, no matter where they are in the building. They expect to be able to just get on the network just like they did at their home, even if they're in the elevator shaft in the elevator. So that's why wireless is important, and that's why we care about wireless so much. So let's move on to how wireless works. So here's some definitions we need to know to understand wireless. So the first one is gain. Gain is an increase in a radio frequency's signal's amplitude. So the examples are an antenna or an amplifier. And gain is measured in decibels. And we're going to talk about decibels in a little bit. But decibels are a relative term, meaning a decibel isn't an absolute value. A decibel is the difference from one thing to another thing. So an antenna might provide 5 decibels of gain. So that antenna is increasing the RF signal's amplitude by 5 decibels over what it was before. Then loss is just the opposite. Loss is a decrease in an RF signal's amplitude. So this can be uncontrollable, such as due to the resistance of cables or connectors because of conversion of AC electrical signal to heat, or intentional through an attenuator. So when you hook up cables and connectors and you go from a, say, wireless card to an amplifier to an antenna, let's say, all those cables and connectors cause loss. So they decrease the signal's amplitude. And that's just because the resistance of the cables as the electrical signal goes over those cables, they cause heat, and that causes loss in the signal's amplitude. And loss is measured in decibels, just like gain. Now, the cables and connectors are unintentional. It's not something you can control that you have loss of a cable. Now, you can select one cable over another cable, one cable that has less loss over the other cable that has more loss. And generally, cheaper, less expensive cables have more loss than a more expensive cable that has less loss. The other way to have loss is intentional through an attenuator. So maybe you have so much power in an amp that you want to slow down the signal or decrease the signal's amplitude and cause some loss. So you put in something called an attenuator that creates loss or lowers the signal's amplitude. Next definition is reflection. Reflection is when an RF wave strikes a large object. So the examples are the surface of the earth, buildings, or walls. So think of reflection just like a mirror. You look in a mirror and you see your reflection. So the light from you is bouncing off the mirror and you're seeing your reflection. And that's what's happening with an RF signal when it goes a long distance over the Earth's bulge, or the shape of the Earth, causes that RF signal to strike the Earth, and then it bounces off the Earth. Same thing if you're sending an RF signal, from one building to another building. Think of in like a downtown metroplex area with lots of buildings. That RF signal is going to strike other buildings and kind of bounce off or reflect. So that's what reflection is. Okay, refraction. Refraction is the bending of an RF wave as it passes through something of different density. So an example of this is an RF wave passing through fog. So this is a serious issue for long-distance RF links. So say that you have two buildings and in between them is a river or a stream. And obviously, some mornings there's going to be some fog above that river due to temperature changes and the water being a different temperature. The fog's going to, rise. And say you had a wireless link that goes through that. Well, when that RF signal goes through that bank of fog, that RF wave is going to bend. It's going to bend off in a different direction because of the density of that air as it goes through there. So that can be a problem with RF links. Obviously, it's probably not a problem in a internal building, or inside a house or a small business, you're probably not going to have fog, hopefully, that the RF signal is going to be bended with. So next term is diffraction. Diffraction is when an RF wave bends as it passes around a large object. So don't confuse this with refraction, because refraction is when it strikes a large object. Now, diffraction is when it bends and goes around a large object. So think about ripples of waves across a pond that go around a boat or a stump in the pond. So you drop a rock in a pond, and these waves start off across the pond. And say there's a stump in the middle of the pond, those waves are going to bend around that stump and continue, but they're sort of in a bended, different shape than they were originally. So that's exactly what happens with diffraction. So to summarize, our three different terms here that are similar but different are reflection, where an RF wave strikes a large object; refraction, where an RF wave bends as it passes through something of a different density like fog; and diffraction, where an RF wave bends as it passes around a large object. So that's the end of our first section. Let's move on to our second section on radio frequency terms. Next on our list of terms is scattering. Scattering is when an RF wave bends as it passes around small objects. Now, when I say small objects, usually we're talking about like rocks or sand that are in the path that the RF signal is taking, or it could even be heavy dust that's in the air. So usually when you're talking about scattering, you're talking about an RF signal that goes outside and it strikes something along its path, maybe some rocks, a driveway that's made out of rocks or something, and when it hits that driveway made out of rocks, it scatters and the RF signal, goes in every different direction. So that's what scattering is. And usually you wouldn't have that inside, or most likely you wouldn't have that indoors. The next term, VSWR, voltage standing wave ratio. This occurs when there's a mismatch in impedance. Now, impedance is resistance to current, and impedance is measured in ohms. So, voltage standing wave ratio occurs when there's a mismatch in impedance between the devices in the RF system. Now, think of this as a large pipe feeding into a smaller pipe. And you put a flow of water into that large pipe, and when it hits the small pipe, there's going to start to be a backup, right? An overflow, kind of like a funnel. You put a bunch of water in the top, and if you keep pouring and pouring faster than the bottom of the funnel can let the water out, you're going to have an overflow, and the funnel's going to overflow with water. This is the same thing. So that overflow, or that return where the water's coming back up the big pipe from where it came from, that's called the return loss. So VSWR is something you have to watch out for when you choose your RF components. So when you choose your connector and your cable and your pigtail and your amp and your antenna, all these different components, you have to look at the impedance of each of those devices and make sure that they all have the same impedance. And again, impedance is measured in ohms. So let's move on to our next list of terms. Okay, next on the list is amplification. And amplification really is the same thing as gain. So we talked about gain, that's increasing the power of an RF signal, and you're talking about doing that, that's measured in decibels. So usually you do that with an amp. An amplifier, you power up an amp and you increase the RF signal. It adds more decibels. There's a greater RF signal, which is more decibels. So amplification is basically the same thing. Okay, absorption. Absorption is when an RF signal is absorbed by material. For instance, a concrete wall. So a concrete wall will absorb the RF signal, and there might be some signal still coming out on the other side of a concrete wall. It happens, but usually a material like a concrete wall will absorb the RF signal, and it just sort of disappears. So that's absorption. Now we have free space path loss. Free space path loss is also known as path loss, or FSL, free space loss. Now this is the loss of an RF signal due to signal dispersion. So this is just the natural loss of the signal over distance. And this is usually in a long distance RF link is where you're most concerned with this. But I mean, even in just a home or a small business, over distance, that signal is only going to travel so far. You can put an access point in a house, take a laptop, and start walking away from it. You might have to go outside, and you might have to go to the house next door or a couple houses down the block before the signal finally dissipates. But it finally will. And I mean, obviously, if you take that access point and you put it outside, it's going to take even longer for that signal to disperse, but eventually it will. And that's the free space path loss. And there's a formula to calculate this, but it's not tested on the CWNA exam, so we're not going to cover it. Let's move down here and look at delay spread. Delay spread is the arrival of the direct signal and the reflected signal at the receiver. So the delay spread is the difference in the time between the first signal and the reflected signal. So at some point, all these things that happen in an RF system to interfere with the path of the RF signal, obviously one of them is reflection, we talked about. And so you're going to have the first signal, and then some part of that signal is going to be reflected, but it'll eventually arrive at the receiver. And the difference in time between when the first signal arrives and the reflected signal arrives, that's the delay spread. So most 802.11b systems can deal with 500 nanoseconds of delay spread, and most 802.11g systems can deal with 150 nanoseconds. So of course, the less delay spread there is, the better the performance you're going to get, and the less interference you have. You don't want that reflection going on, so you don't really want any sort of delay between those signals at all. But naturally, with all the different obstacles that are going to be between a sender and a receiver, you're going to have some sort of delay spread, and that's pretty normal. Hopefully it's just not a lot. Let's move on to RF math. Okay, in RF math, let's go through some terms here. The first one is watt. A watt is 1 amp, or A, represented as A, at 1 volt. So 1 amp at 1 volt is a watt. Now this is the pressure of the current, or the pressure of the RF signal, the flow. So if you were to think of it as a water hose, and you turn on the water just a little bit, it's just going to trickle out of the hose. So there's not a very strong flow or current on that water. So the watt would be the measure of that if it was an RF signal. Obviously not the measure of it if it's water. But if you were to crank up the handle a lot, you would get a real strong flow or current through that. So that would crank up the watts. So it's not the power, but it's the pressure. The pressure, how fast that signal is coming, or how strong that signal is coming. Okay, next one is milliwatt, and that's abbreviated MW. And a milliwatt is 1/1000th of a watt. So we know what a watt is. This is just 1/1000th of a watt. And most APs run at 30 to 100 milliwatts, and most wireless cards or adapters run at 15 to 30. So I have a card that runs at 200, and it doesn't even have an antenna on it. So you can get various power levels of cards and access points as well, and that's going to play a part in how good a reception you get and how far away you can pick up things that are wireless networks that are far away. Obviously, if you have a card that only runs at 15 milliwatts, you're going to have trouble picking up an access point that's a couple buildings down or next door, versus if you had a card that runs at 200 milliwatts, you've got a lot more flow or pressure to your signal to try to pick things up. So, and then the last one on this list is decibel, and that's abbreviated dB. And decibel is a relative measurement of power, and it's the power difference between one thing and another thing. So it's a comparison. So if someone were to say, what's the decibel of that card? Well, you have to say, compared to what? You know, because a decibel is a comparison to something else. So there's a formula for it here. You see this. The power difference in decibels equals 10 times log power A divided by power B. You know, we don't have to know that for the CWNA, and that's not something that most, wireless engineers have memorized. But the important thing is that it's a comparison between two things, and usually it's between, you're comparing milliwatts. So this and the power of A in milliwatts and the power of B in milliwatts gives you the decimals, so you can compare the difference between those two. And we'll talk more about decibels in a little bit. So let's move on to RF math number 2. This is called the tens and threes of RF math. So for every 3 decibels you take away, right here, you have to cut the power in half. When you're talking about milliwatts here, you cut the power in half. For every 3 decibels you add, you double the power in milliwatts. For every 10 decibels you take away, you multiply the power in milliwatts by 1/10, or it's 1/10 the power. For every 10 decibels you add, you get 10 times the power in milliwatts. So how you can use this is for every 3 decibels that are taken away, you divide the milliwatts by 2. For every 3 decibels you add, you multiply the milliwatts by 2. For every 10 decibels you take away, you divide the milliwatts by 10. And every 10 decibels you add, you multiply the milliwatts by 10. And don't get in a panic right now. We're going to use this in formulas. We're going to do it in use this in sample problems so you can get familiar and figure out how this works. But you can actually combine the tens and the threes together. So if you had 13, say you were adding 13, you would multiply by 2, then multiply by 10. So you can use these together. So let's do some sample problems so you get a hang of how this really works. Okay, so first sample problem is a 20 milliwatt signal is transmitted to an amp, and the amp adds 10 dB of gain. What is the strength of the output signal? So remember, the 10 dB of gain, that's a relative term. So you started at 20, and you're adding this 10 dB of gain. So what does that do to the milliwatts? That's what you're trying to find out is, how many milliwatts did you get out of it? You started with 20, the amp adds 10 dB of gain, and how many milliwatts are you getting out of it? So the 20 milliwatts plus the 10 dB of gain, the 10 dB of gain means to multiply by 10. So if we go back here and look at our formula, plus 10 dB means multiply by 10. So 20 milliwatts times 10 is 200 milliwatts of output power. So by taking the 20 milliwatt signal, adding the amp, you got 200 milliwatts of output power. So these are the types of problems that you might find on the CWNA exam. So it's good to understand how to do these and practice some of them yourself. So let's do another sample problem. So this one says a 300 milliwatt signal goes through an attenuator. And remember that an attenuator is what you put in to reduce the amount of signal or create loss. So it says that that adds 3 dB of loss. So what's the output signal? Well, if we look up 3 dB of loss, or negative 3 dB right here, it says to divide by 2. So let's go back. So the 300 milliwatts divided by 2 gives you 150 milliwatts of output power. So you start off with 300. The attenuator added 3 dB of loss. That meant divide by 2. So you got 150 milliwatts. Okay, let's move on. So here's another sample problem. In this sample problem, it says a 200 milliwatt signal is transmitted to an amp, and that amp adds 6 dB of gain. What's the strength of the output signal? So 6 dB of gain, you're thinking, that wasn't a 10, and that wasn't a 3. So what we have to do is we have to take 2 3s. So if we look over here at our math chart here, when you add 3 dB of gain, you multiply by 2. So what that means is we're just going to have to multiply by 2. Then we're going to have to multiply by 2 again. So let's go back and try it. So you start off with 200 milliwatts. We added 6 dB of gain. That means to multiply by 2, then 2 again. So that gives you 200 times 2 will give you 400. Then 400 times 2 again would give you 800 milliwatts of output power. So that's what the amp was able to give you by adding the 6 dB of gain, was 800 milliwatts of output power. Let's try another one. So you have a 300 milliwatt signal that goes through a cable, and that cable has 13 dB of loss. So what's the output signal? So this 13 dB, to calculate that, we're going to have to take 110 and 13. So if we go back here, and we're talking about loss, so a 3 would mean divide by 2, and then a 10 would mean divide by 10. So let's go back and do our problem. So we start off with 300, we divide by 2, that gives us 150 milliwatts. Then we divide by 10, and that gives us 15 milliwatts of output power. So we started off with 300, the cable added 3 dB of loss, so we had to divide by 2, then divide by 10 to give you 15. Now you can use these types of calculations to calculate the whole RF system, and that's the sort of thing you need to know when you go take the CWNA exam, is how to calculate the whole thing. So if you had a cable that had 13 dB of loss, and an amp that added 6 dB of gain, and an antenna that added 10 dB of gain, let's say, these are all just numbers I'm making up, what's the total output? So that's how you use these numbers. So let's move on to our next set of slides. Our first term here is dBm. Now we said that dB is not an absolute value. It's a comparison between two things. So you have to have two things to compare before you can, say what the dB is between them. Here's a useful term called dBm, and this is decibels when compared to 1 milliwatt. So this is an absolute value. So if you said, I've got an RF signal, but don't know the signal strength, let's say, you put in this amp, and the amp is going to add, say, 6 dBm. How many milliwatts is that amp, adding? Well, you could use the dBm calculation to say, when compared to 1 milliwatt, this amp is adding so much more power. So it is an absolute calculation, and there's formulas to convert things back and forth, and we can do that here in a little bit. Okay, next one is dBi. dBi is a measure of dB when compared to an ideal antenna. Okay, the ideal antenna that they're comparing it to is called an isotropic radiator. Now, there really is no perfect ideal antenna, but the sun is an example of an isotropic radiator, as if you took measurements around the sun on each side of it, in general it radiates its energy perfectly in every direction. So it's an example of an isotropic radiator, but there really is no antenna that we can buy that is a real isotropic radiator. So all the antennas can be compared to what an isotropic radiator, would radiate. So real antennas, they radiate energy in one direction or another. And, when you hold up an antenna, you picture that energy, going in whatever direction you point the antenna. But in reality, it really doesn't radiate in that direction. And we're going to talk about antenna radiation patterns and stuff here in a little bit. But let's say here that an antenna that radiates 10 times as much energy in one direction as an isotropic radiator would have a gain of 10 dBi. So it's a comparison to that isotropic radiator. So this antenna radiates 10 times as much energy as an isotropic radiator, so it has a gain of 10 dBi. And the gain of antennas is usually measured in dBi. That's usually what dBi is used for, is for antennas. So let's go on to a couple more. dBd. A dBd is a measure of decibels relative to a dipole antenna. A dipole antenna is a certain kind of antenna, and that type of antenna, a dipole antenna, has 2.14 dBi of gain. So thus you can convert dBd to dBi by adding 2.14. Okay, so dBd is decibels relative to a dipole antenna. And then the last one on the slide is RSSI, which is the received signal strength indicator. Now this is shown in, Windows or on a PDA or on a Linux machine, the little pattern of bars in the bottom that shows you your wireless signal strength. Now a lot of people look at that and, it is important to know how strong your signal is, but what most people don't know is that there's really no standard for that received signal strength indicator. There's no math measurement, and every vendor who makes a card and who makes the drivers can calculate that differently. So it doesn't have to be based on one thing or another. One vendor's card, although it might say it has 4 bars, another vendor's card might have 5 bars. The 4-bar, receive strength indicator might be actually getting a better signal than the one with 5 bars, and that's because the vendors are measuring that in different ways with different calculations. So you can't really tell a lot by those receive signal strength indicators other than, looks good or looks bad, but you really have to get some more higher level, better quality wireless tools to really tell you the exact calculations and the exact signal strength in real numbers from what you're getting through a wireless network. So we'll talk about that more in the troubleshooting section of these videos. Let's move on. In this sample problem, it says that a 100 milliwatt signal is transmitted from an access point. How many dBm is that? Well, we learned that dBm is decibels per 1 milliwatt, or a decibel compared to 1 milliwatt. Because a decibel is a relative term, you have to compare it to something. So a dBm is compared to 1 milliwatt. So to take 1 milliwatt and turn it into 100 milliwatts, what do you have to do? Well, you have to take the 1 milliwatt, multiply it by 10, that gives you 10, and then multiply the 10 by 10, and that gives you 100 milliwatts. So each multiply by 10 is 10 decibels. So thus, we added 20 decibels total. So the answer here is that 1 milliwatt plus 20 decibels is 100 milliwatts. So the original question was, a 100 milliwatt signal is transmitted from an access point. How many dBm is that? Well, the 100 milliwatts is really 20 dBm. 100 milliwatts is 20 dBm. And we did that because we could multiply by 10 here and multiply by 10 here to make that 1 milliwatt, which is 1 dBm, into 100 milliwatts. So each of these, when added together, makes the 20 dBm. That's how much we had to change the 1 milliwatt to make it into 100 milliwatts. So that's how you calculate dBm. Okay, here's our next set of definitions here in terms. The first one is system operating margin, or SOM, and this is also called the link budget. Now this is calculated by adding together all the gains and losses between the sending station and the receiving station. So you have two stations. In between the two stations they have maybe all these different wireless components. They have an adapter on the client. Maybe the adapter goes to an antenna. Maybe there's a cable between those two. Then from the antenna it goes to an antenna on the other side on the access point. Then maybe a cable, and then finally to the access point. Maybe there's an amp in there somewhere too. So to calculate the system operating margin, which is also known as the link budget between all those two systems, you take all the gains and losses, usually in dB, we're talking about all the different gains and losses, and you calculate up the system operating margin. Okay, next one is fade margin. The fade margin is the extra signal strength added to the link budget to allow for inconsistent signal. So between those two, the sender and the receiver, there's going to be some inconsistent signal. You're not going to, have a perfect signal all the time. So the fade margin is the extra signal strength you add into the link budget to allow for that inconsistent signal. Intentional radiator. An intentional radiator is defined by the FCC, and that includes all parts of an RF system but not the antenna. So the adapter, the cable, the amp, the other cable, all that stuff is part of the intentional radiator, but the antenna itself is not included. Okay, the equivalent isotropically radiated power. Wow, that's a big one. It's down here. Equivalent isotropically radiated power is EIRP. Now, the EIRP is the RF power radiated by the antenna. So the actual power that's coming out of the antenna, that's created by the card and the cable and the adapter and the antenna, all that stuff, that's called the EIRP. Now, the law in the United States is that for a fixed point-to-point antenna, so you got two buildings, you want to connect them, you have this fixed point-to-point antenna that connects the two buildings, you cannot exceed 4 watts. 4 watts of total EIRP, the total output of the antenna on each side, cannot exceed 4 watts. Now for an omnidirectional antenna, so say like an access point at a business or out in a warehouse or out in a yard maybe, or a manufacturing plant, say you have a big amp on it and an antenna, so you're trying to give as much coverage as possible. So the omnidirectional antenna means it's not at a fixed point, it's not unidirectional, it's omnidirectional, it goes in all different directions. So that cannot exceed 1 watt. So these are defined by the FCC, and these are the laws in the United States at least. So let's look at an EIRP calculator. This is one I found on the internet. So this calculator has some instructions, talks about EIRP, talks about decibels. Let's just go down here and just fill in a sample number. Say we have a 1 watt actual transmitter power output. Just leave the default antenna gain of 5. We'll click calculate. Scroll down and it says our EIRP is 3.16 watts. So if we go back, 3.16 watts, we're not exceeding the fixed point-to-point antenna configuration, but we are exceeding the 1 watt omnidirectional antenna law put out by the FCC. So there's other calculators on the internet. You can type in gain and loss of the different cables and parts, and it'll calculate it all for you. So this one's a pretty basic one. There's a lot of different neat ones you can use out there. So on to the next term here. This is the 6 dB rule. And the 6 dB rule says for each 6 dB increase in EIRP, the range is doubled. So if you had a wireless access point set up and you walked out to a certain point with it and tested it with a laptop, tested the range with a laptop, you could see, where your range was. If you said, well, that's not enough, I want to double that range, well, you need to increase the EIRP by 6 decibels. So that's exactly what you need to do. Now how you do that exactly is up to you. You could use an amplifier, you could use a different antenna, or whatever, and then you could use a calculator to calculate what your new EIRP would be. So let's move on to signals and antennas. So our first definition under signals and antennas is visual line of sight, or it could just be called line of sight. And the visual line of sight is the apparently straight line of sight. And it's apparently straight because light waves are subject to refraction, diffraction, and reflection. So if you stand up on top of a building and you want to create a point-to-point wireless link between those two, you look out and you have line of sight, let's say, you can see the top of the other building, but that's an apparent line of sight, meaning the actual RF signal might deviate from what you think is the straight line of sight. And that's because light waves are subject to refraction, diffraction. So the light waves that you're seeing that look like the line of sight to you might be different than the actual RF line of sight. So then there's the RF line of sight, and that's the line that the RF signal is going to take. So the RF line of sight can be blocked by the Fresnel zone. And that's the next term here, Fresnel zone. And the S is actually silent, so it's pronounced Fresnel. I know it's kind of strange. It's strange to me, but that's how it's pronounced, Fresnel zone. And the Fresnel zone is the area around the visual line of sight. So if you look at this little picture here, here's two antennas, two wireless antennas, and then there's this dotted line here, and that represents the line of sight. But the Fresnel zone is this area around the line of sight, or around the RF line of sight. So you have to make sure that this Fresnel zone is clear. Even though the line of sight might be clear, if there's things down here like houses and trees and hills and stuff, and they're in the Fresnel zone, they can block out part or all of the wireless signal, even though it looks like you have line of sight. So you have to allow for a lot more area around the RF line of sight than just the straight line. So let's talk about water. Water absorbs radio frequency signals. So that's why you can send an RF signal through walls, but it's very hard to send it through trees, and that's because the trees have water in them. So microwave ovens, like you have in your kitchen, they work at 2.4 gigahertz too. And the energy that's absorbed by the water in the food is how the food is heated. So there's water in the food you put in the microwave, and those 2.4 gigahertz microwaves hit that water in the food. The water absorbs the energy and it turns into heat. So that's just an example of how water absorbs that energy. So it's very easy to secure a wireless LAN in a submarine or a swimming pool because the water around those things absorbs the RF signal. And there's no chance for an attacker to eavesdrop on the signal that's surrounded by water because the water absorbs that signal completely. So you might have a tough time, though, selling that as a security measure to a company. Just surround your building with water and you won't have a problem. Could be a tough sell. But it is very interesting how well water absorbs RF signal. Then let's talk about how the Fresnel zone is three-dimensional. And the picture doesn't really show that. It looks like it's a big flat blob here, but really it's a three-dimensional object. And there's a formula to calculate the Fresnel zone. And the Fresnel zone is about 60% of the unobstructed radius around the visual line of sight. But the formula is not part of the CWNA exam, so we're not going to cover it. But just so you know, this is a three-dimensional area. So let's talk about beam widths. Beam widths are the width and height of the antenna's beam. So when you think of an antenna on an access point or a wireless client, it might look like a straight up and down stick, but really that antenna, the signal that comes out from that antenna has a certain shape. It's not a straight line like a laser. It's not a flat line or a line that stands up and down. It's kind of a big blob, and it all depends on the type of antenna you're using, but that big shape that comes out from the antenna with the RF signal is called the horizontal and vertical beam width. Now this beam width can be measured, and they call it the azimuth and the elevation. So the azimuth is the top-down view of an antenna's coverage. And you can see down here, this is a picture of an azimuth drawing. So here is an antenna, and then this is the shape that the antenna's signal took if you look at it from the top down. Then the elevation is the side view of an antenna's coverage. And so this down here, this H-plane side view, this is a side view of what the antenna looked like. So here was the antenna, and this side view is what it looked like from the side. So that's the azimuth over here, top down, and the elevation. Now these planes are called the E-plane and the H-plane. Now, passive gain versus active gain. Passive gain is where gain is achieved by an unpowered antenna. So you take a wireless card, you stick an antenna right on the end of it, and that's passive gain. You had the strength of the signal from the RF card, or the wireless adapter, and then you put an antenna on it, and the antenna is unpowered. It's just shaping the RF signal. But that's the only way it's creating gain, is by shaping that signal, and that's passive gain. Now, active gain is by taking, say, the same wireless adapter, but then adding a powered amplifier to it, and then connecting that amp to an antenna. That's called active gain. You're increasing the power with something other than just the antenna. So that's the difference between passive gain and active gain. All RF waves have the following properties. Okay? Polarization. Polarization is the first property. Polarization is the physical orientation of the antenna in the horizontal or vertical position. So horizontal position is where the electrical field is parallel to the ground. So it runs right along with the ground. That's horizontal polarization. Vertical polarization means the electrical field is perpendicular to the ground. So they cross each other like a T. That's perpendicular. And that's a vertically polarized antenna. Now most access point antennas are vertically polarized. So you think of your little access point, it's got the two little antennas sticking straight up from it, right? So those are vertically polarized antennas. The long-distance wireless LAN antennas are horizontally polarized, and that's because they're meant to go along the ground a long distance. So they're horizontally polarized. Now, the plane that's parallel with the antenna, that's called the E plane, or the electrical or elevated plane. The plane that's perpendicular to the antenna is referred to as the H plane, or the magnetic or azimuthal plane. That's hard to say. Azimuthal plane. So make sure the two antennas are mounted with the same polarization. So if you think about a laptop that's got a PCMCIA card in it, and then you've got an access point, really the access point antenna should be turned horizontally to match the PCMCIA card's built-in antenna, because the PCMCIA card, think of your laptop sitting on the desk, the card's in the side of it, the antenna is going back and forth left to right, just like the keyboard on the laptop. Whereas the antenna on the access point, most people stick those straight up and down. Well, really they need to be turned sideways to match the polarization on the laptop's card. There's different ways to do that, obviously, and most people are relatively near to their access point, but that can make a difference if you're having a problem. Might be the polarization of the antenna. So let's move on to amplitude. Okay, amplitude is the change in RF energy. So think of this as the power of the RF wave, such as 200 megahertz versus 50, or 200 megawatts versus 50 megawatts. Think of this as the size of the wiggles. So if you look at this down here, see how much these lines are going up and down, those are the wiggles. So the amplitude, that's the amplitude right there, the size of those lines. So this is a picture here that shows high amplitude, medium amplitude, and then low amplitude. Okay? Frequency, wavelength, and phase are all based on a signal's amplitude. So that's what we're about to talk about right now is frequency, wavelength, and phase. And they're all based on the amplitude. Okay, wavelength. Wavelength is the distance in between the peaks of a signal. So an antenna is what creates a wavelength. The wavelength will be the same as the size of the antenna. Next term is frequency. Frequency is the number of times that a signal's amplitude peaks. That is its frequency. So frequency is measured in hertz, just like 2.4 gigahertz. That's its frequency right there. Last term on this slide is phase. Phase is the measure of whether or not two signals are in sync. So in other words, if you laid a picture, just like this picture we had up here, if you laid a picture of the two RF signals on top of each other, would they match up? And phase is measured in degrees like a compass. So up here, here's 3 different amplitudes and 3 different phases. These phases don't match up. They're not the same. But if you took 2 pictures that both had this exact same high amplitude here, you laid them on top of each other, their phase would match up. They're exactly in sync. That's phase. Okay, let's move on to spread spectrum. Okay, spread spectrum is used in all different sorts of wireless networks. Wireless LANs, PANs, MANs, and WANs. So what are all those things? Well, a wireless PAN, or WPAN, different pronunciations are available of it, but a wireless PAN is a wireless personal area network, and that uses Bluetooth. So think about your Bluetooth headset and your Bluetooth cell phone, and you got your cell phone in your pocket, you're making a phone call, you're talking on the phone with your Bluetooth headset. You're creating a wireless personal area network. Next one is wireless LAN, and that's the one we're most familiar with, a wireless local area network. Uses 802.11, 802.11b, G, whatever. You got it in your home, in a small business, in a large business, campus, over at the local coffee shop. That's a wireless LAN. Okay, wireless MAN, or wireless metro area network. Now these usually use the 802.16 or 802.20 standards that are built for wireless metro area networks. So a wireless metro area network is a wireless network that goes around a city. So around a large city, say the city of Chicago, let's say they take that and they make a wireless MAN that goes all the way around the city and connects all the city offices and buildings and all the city infrastructure for management. So they created a wireless MAN. Okay, last one is wireless WAN, or wireless wide area network. Many times this is done with 802.11, can be done with different things. Basically, a wireless WAN is a wireless connection between two cities or between two very long distances. And there's a lot of wireless internet service providers out there, and they do this. They connect, large buildings in one city with another, one of that company's offices in another city using wireless. That's a wireless WAN. Okay, now on to some spread spectrum technologies. Let's scroll down and look at those. Okay, frequency hopping spread spectrum, FHSS. FHSS is not used by 802.11. In fact, it's not very popular at all, but it is one of the methods of spread spectrum technology. Now, just like it says, it does frequency hopping. So it goes from one frequency to another, and it stays on each frequency a certain amount of time, and this is all predicted by the access point and the card. They know how long each of the transmissions are going to stay on each frequency, and that's called the dwell time. How long they stay on there, that's the dwell time. And then they hop and they move to another frequency. And for a small amount of time there, there's no wireless connectivity at all. And the time that it takes to move from one frequency to another frequency, that's called the hop time. So the great thing about FHSS is that it has great immunity to interference. So if on one of those frequencies, if there's a lot of interference going on, it's constantly hopping from one to another. So because of that, it doesn't get interference like other wireless technologies do. Next up is direct sequence spread spectrum. Now, DSSS is popular in wireless LANs because it's used by 802.11b. It's not used by 802.11g or A, but 802.11b. So let's look at the channel layout of 802.11b and direct sequence spread spectrum. So I'm going to scroll down here a little bit, and this is a diagram here that shows some of the different channels that 802.11b runs on. Well, actually, all the channels that 802.11b runs on. And what the diagram shows here is that this wireless device is set on channel 3. And this is the megahertz in here that it runs on. And if let's just scroll down here for a second and look at this little chart. So here's the different channels, channels 1 through 11. These are used in the United States. Other countries might have other channels. But say, for instance, like channel 3, its center, the center for its signal is 2.422 gigahertz. The low end is 2.411 gigahertz. And the high end is 2.433 gigahertz. And if you go up to this graph here, this graphic, you can see that. So here's 2.422 gigahertz right here in the center. And as you can see, it goes down on each side, but there's a lot of bleed over from just one station being on channel 3 to actually all the other channels. So that's one of the problems with direct sequence spread spectrum, is it bleeds over to all the different channels. So if we scroll down and look, one of the things here that I want to point out is that channels 1, 6, and 11 are the only non-overlapping channels. Or there has to be a 25 megahertz spacing between the channels for them not to be overlapping. So if you look here at channel 1, here's the center, 2.412 gigahertz. channel 6 is 2.43 gigahertz. So the difference between those two right there is 25 megahertz. That's the difference between those two. So there has to be 25 megahertz in between the channels for them not to be overlapping. And in fact, in some instances, even channel 6 can overlap with channels 1 and 11. And it depends on the EIRP, or the antenna and the amp that you use. The output strength of that might even overlap with other channels. So, but that's what the channel layout looks like right there. And this station's set on channel 3. So let's scroll on down here and let's talk about another spread spectrum technology, and that's OFDM, or orthogonal frequency division modulation. So OFDM, it's a lot easier to say it that way. OFDM is popular in wireless LANs because it's used by 802.11g. Now OFDM is better than DSSS because it's faster and it gets less interference. So if you're using 802.11g, you're going to have less interference than you would if you're using 802.11b. So OFDM uses harmonics from digital signal processors, or DSPs, to tune the signal to be able to use a single channel and place many smaller streams of data in that channel. So it can more accurately tune in on a single channel, and then inside that channel, it can place smaller streams of data. So it's kind of like multiplexing. It takes one channel and it turns it into multiple streams. And that's how it's able to get so much more bandwidth. That's how 802.11g is able to get 54 megabits instead of 11 megabits like 802.11b. And it also gets less interference because it uses those harmonics from the DSPs. Okay, 802.11a also uses OFDM, but it does it in the 5 gigahertz range, whereas 802.11g, of course, is in the 2.4 gigahertz range, just like DSSS or 802.11b. Now, for an 802.11g system to be backward compatible with an 802.11b system, it really just runs two radios, one that's doing OFDM and one that's doing DSSS. So 802.11g really isn't backward compatible with 802.11b. They just, for the standard, the 802.11g standard, they require it to be backward compatible. So they put both things in the same access point or wireless card, and that's what makes it seem like it's backward compatible. Now, spread spectrum works by modulation and coding. Coding and encoding is how the data is represented in ones and zeros. So that's what coding is. Modulation is how the signal is used to represent the data. So examples of different modulations are amplitude modulation, frequency modulation, and phase key shift modulation. So those are different modulations, different ways that the RF signal, like up here, is used to represent the data. And the coding and encoding is just how the data is represented in ones and zeros. Now here's some more definitions. First off, the IEEE is the Institute of Electrical and Electronics Engineers, and their website is IEEE.org. The IEEE is what creates all these standards. The 802.11 standard, B, G, all the different letters. 802.3 is Ethernet. There's a lot of 802 different standards for all different sorts of technologies. But mainly we're talking here about 802.11 or anything that any standard after that, like 802.11b, G, A, X, Y, Z, whatever. So first let's talk about the 802.11 standard. Now it was ratified in 1997 and it was updated in 1999 and 2003. 802.11 details DSSS, FHSS, and infrared. DSSS operates at 1 to 2 megabits only. So if you're just talking about using 802.11 equipment without any letters after it, and you're using DSSS, you're talking about 1 to 2 megabit data rates. DSSS and FHSS systems must run in the 2.4 gigahertz area, And the 1.2 or 1 to 2 megabit DSSS systems are called Clause 15 systems. And that's just because they're described in Clause 15 of the 802.11 standard. Okay, we got all sorts of alphabet soup here with 802.11. So next, let's talk about 802.11b. 802.11b runs at 11 megabits. It uses DSSS, or direct sequence spread spectrum, and these are called Clause 18 systems, and that's because they're defined in Clause 18 of the 802.11b standard. Now they must interoperate with Clause 15 systems, which is the regular 802.11 equipment that runs at 1 to 2 megabits. Next up is 802.11a. Now 802.11a uses OFDM. It runs in the 5 gigahertz range, and it runs at up to 54 megabits. And these are called Clause 17 systems. Now they're not compatible with 802.11, 802.11b, or 802.11g systems, and they have a shorter range than those systems. 802.11a is a great technology, but it just hasn't been as popular as 802.11b or g. Next up is 802.11g. So 802.11g uses OFDM. It runs in 2.4 gigahertz. It runs at up to 54 megabits. Although some manufacturers have created their own equipment that they say will double that data rate. Like one manufacturer has 108 megabit cards. And really what they're doing is they're using multiple 54 megabit streams to do that. But that's a proprietary technology, and that's not a standard. 802.11g only runs at up to 54 megabits. And it's required to be backward compatible with 802.11b and 802.11. Another standard is 802.11d. Now this is for FHSS networks, and it's for usually countries outside the United States where they want their wireless stations to be able to change the MAC layer to specify country-specific information. And as FHSS is not very popular, neither is 802.11d. 802.11e is for quality of service. That's right here, quality of service. It's for wireless LANs, and it's a draft standard as of July 2005. So this isn't yet a full standard, but a lot of people are looking forward to 802.11e because the quality of service that's required for voice over IP and for gaming applications. So people want to be able to surf the web, talk on their voice over IP phone, and maybe play a internet game all at the same time. And all of those take bandwidth from your internet connection. So the catch though is that the gaming system and the voice over IP, they have a high need for quality of service. So they're not very tolerant to latency, meaning they can't tolerate delay on the network. So if you're downloading something big from your computer, it could slow down your voice over IP connection to the point where your voice over IP sounds really, really bad. Same thing with the gaming. It could slow down the voice over IP, or the gaming can be slowed down by something else and your game grinds to a halt. So that's why people want 802.11e. But it's coming soon. Next up is 802.11f. And this is access point handoff for roaming. Now some manufacturers have come up with their own way of doing access point handoff for roaming. Roaming's important if, say, you have a PDA and you're walking and you're moving from access point to access point. You want to be able to roam. But more importantly, if you're talking on a voice over IP phone that you're walking around the building with and it's talking to access points, just like your cell phone, you know, when you're driving down the road, you're able to roam from cellular tower to tower. Same thing with an access point and a voice over IP phone. You want to be able to roam from access point to access point as you're walking around a large campus building. And that's what 802.11f is supposed to be able to do. I told you we had a lot of different letters here. Next up is 802.11h. This is in the 5 gigahertz spectrum, and it's dynamic channel / frequency selection, DCS / DFS, and transmit power control, TCP, for European compatibility. and it doesn't come into play in the United States. So if you're in the United States, don't have to worry about that. Now 802.11i. This was ratified in June of 2004, and it's stronger security for the wireless LAN. It's also known as WPA2, or Wi-Fi Protected Access 2, and we're going to configure WPA2 very soon in one of the upcoming videos. It uses AES and CCMP, and it can be used in personal mode or enterprise mode. In personal mode, it's called pre-shared key, or that's what you put in to authenticate you to the network. In enterprise mode, you're using 802.1x, and we're going to configure 802.11i with enterprise mode later in the video series. It's very cool stuff. Now let's move on to 802.11j. This is really in Japan, and it has no effect on the US. So we're going to move on. Just one of the other 802.11 standards that you should have heard of, hopefully. Now 802.11n. A task force was formed in January of 2004 for a new data rate standard. It's supposed to be up to 10 times faster than 802.11g. That would make it up to 540 megabits. So that's pretty fast. That's half a gig wireless. Now right now they're trying to figure out what the real standard's going to be, because there's two competing standards that vendors have come up with. There's the WWISE, the Worldwide Spectrum Efficiency, and there's the TNG Sync. Both of these are come up from two completely different vendors, so those vendors are kind of battling for which one's going to be the standard. Now 802.11n uses MIMO, which is multiple inputs and multiple outputs, and OFDM. Okay, 802.11s. This defines standards for mesh networking. So mesh networking would be, say, on a campus, you have multiple wireless access points talking to each other, all creating one network. It's an example of mesh networking. And yes, there are even more 802.11 standards, but this is plenty for you to know about to prepare for the CWNA and just to be up to date on all the different 802.11 standards. So when you're out there shopping for wireless equipment, you know what to look for. You pick up the box and it says it supports 802.11i or n or whatever. You need to know what that is. And then finally, the Wi-Fi Alliance. This is a group that promotes, tests, and certifies wireless gear for interoperability. Their website's wifi.com, and really what they do is they just test to make sure that different vendors' equipment works with other vendors' equipment. And then when it's certified that it will work, they get a little logo, Wi-Fi Alliance logo sticker on the outside of the box. And they do have some different standards, like one for security and one for interoperability and so forth. You can learn more about them at their website. Okay, now let's talk about some definitions, some more definitions. Active scanning, or probes. These are when stations send a probe that they want to join the network. That's what an active scanning probe is. Next is passive scanning. This is in the form of beacons. Beacons are sent by an access point or an ad hoc client specifying the network BSSID, or the Basic Service Set Identifier, that they're offering. So basically the access point saying, hey, here I am, here's my beacon, this is what I have. Active scanning is a probe by the client saying, hey, I want to join a network. Okay, moving on to dynamic rate selection. DRS is the method for dynamic speed adjustment on a wireless LAN based on signal quality. So just like when you connect, say, with a dial-up modem, you hear that initial handshake where the two modems negotiate the connection. I'm sure anybody who's ever dialed up to the internet has heard that. And I know that's old technology, and hopefully you don't have that, you have something faster. But that's an example of negotiation, speed negotiation. Next up is DCF modes. Let's scroll down to that. DCF modes are distributed coordination function. It's safe to assume that DCF and CSMA-CA are the same. And we're going to talk about CSMA-CA in a second. Basically, if any station is using a wireless LAN, all other stations must wait. So the distributed coordination function goes along with CSMA-CD or CSMA-CA. And that's what wireless LANs use to determine who can talk on the network. So How it works is while one station's talking, all the other stations can hear that, and they have to wait. They just have to wait until that first station is done. And on a network that doesn't have a lot of stations or is not very congested, that works fine. But if you get a lot of stations on a wireless network or a lot of congestion, you can start to have problems, obviously, because the stations have to wait and maybe they never get a turn to talk. So here's some other modes that help that. PCF mode, point coordination function, and that's where DCF doesn't guarantee timely access, PCF does. So you can change from DCF to PCF, one of the more advanced features you might look at changing on a wireless LAN. We mentioned CSMA-CA. This is what wireless LANs use to determine, who can talk when. So this is used on 802.11 networks, and all senders must wait until the current sender is done. CSMA-CD, on the other hand, is carrier sense multiple access with collision detection. This is used by Ethernet, and it's an improvement over CSMA-CD, and that's because the stations can tell when there is a collision. When two stations have tried to talk at the same time, that's a collision. So the stations can tell when that happens, and then they can retry at a set interval. RTS, CTS, and CTS to self. These are flow control mechanisms that can be enabled on wireless LANs. And that's really all you need to know. Unless you want to go read a lot more about those, you're welcome to. Fragmentation. Fragmentation is just taking large frames and turning them into smaller frames to be sent across a wireless LAN. On the receiving side, whatever was fragmented has to be reassembled and put back together. So an example of this is, say you're trying to move something that's really huge, a huge piece of furniture, maybe to make it smaller to fit in your car. You take it apart, and when you get to the place you're taking it to, you put it back together. Just an example of fragmentation and reassembly. And any kind of network does this all the time. An Ethernet network, wireless network, either one, they're always taking large packets apart, sending them across the network, and putting them back together. Last on this list, we have Wireless Multimedia Certification, or WMM. This is a certification by the Wi-Fi Alliance that this product that they certify supports quality of service. And this is even though that that product may not support 802.11e, the new standard for quality of service. WMM is a certification by the Wi-Fi Alliance that it supports this subset, or this WMM subset of 802.11e. So it's sort of an interim standard, an interim certification until 802.11e is ready. The Wi-Fi Alliance is pushing this WMM. 802.11e is going to replace DCF and PCF. Next, let's move on to types of wireless networks. Now, here's some different types of wireless networks you should be aware of. First off is BSS and the BSS ID. A BSS is a basic service set. Now, this is the building block of a wireless LAN. The BSS ID is the basic service set ID, and that's what identifies the BSS. The BSS ID is a 48-bit hexadecimal number. Now, in infrastructure mode, the BSS ID is the MAC address of the access point. So normally, that's what you're going to be using in most wireless networks, is what they call infrastructure mode. Infrastructure mode just means you have an access point in the center and you have clients connecting to the access point. So in infrastructure mode, the BSS ID is the MAC address of that access point. And the BSS is that basic building block is the access point and the wireless network around it. That's the BSS, the basic service set. Now, an independent basic service set, or an IBSS, is an ad hoc network. An ad hoc network is just a connection between two clients. Two clients want to talk directly to each other. That's an ad hoc network, and it's called an IBSS. Now, ESS and ESSID, or the SSID, is an extended service set. The ESS is the extended service set. Now, two or more BSSs that share the same SID, or the same SSID, which is two access points with the same SSID, forms an ESS, or an extended service set. So an ESS is just more than one BSS, but they have to have the same service set identifier, the same network name, if you will. So a SSID or an ESSID, same thing, is an alphanumeric value from 2 to 32 characters. And that's the network name right there. That's how you identify the network you're connecting to. The SSID must match between client and access point. The ESS is used in infrastructure mode, so an ESS is made up of multiple BSS. Now, a multi-BSS is really virtual access points. This is a feature that's available on enterprise-grade access points. It's not something you would find on a regular off-the-shelf, lower-end access point. Now, what multi-BSS does is it's one access point that can advertise multiple service set identifiers and has multiple BSSs all built in. So it's kind of like one access point that can simulate multiple access points. Or really not simulate, but is multiple access points all in one. So you can connect to different networks. One could be a private network that goes just to the internal LAN, maybe a highly secure network. The other one could be a public network that just goes right out to the internet. And you could do all that with just one access point. And then finally, roaming. We talked about roaming, just like a cell phone, moving between access points and how important that is. But there is seamless roaming versus regular roaming. Regular roaming just means you can disconnect and you can reconnect, and so you are able to roam. You are able to move from access point to access point. But mainly when we think about roaming, like on our cell phone, we're talking about seamless roaming, which just means you can walk from cell to cell or access point to access point and never even notice any kind of blip in your network connectivity. That's seamless roaming. Okay, here we are on authentication. Now the first step to getting on a wireless LAN is called authentication. 802.11 specifies two authentication mechanisms, either shared or open. Open authentication means there's no key to authenticate, but it goes through the process. All they have to have is the same service set identifier. So basically an open authentication network really means there's no authentication, anybody can get on it. You don't have to have anything except the service set identifier. You have to know what network you're trying to connect to, but you don't need any credentials. Then there's a shared key network or shared key authentication. This is where the web key or the wired equivalent privacy key is used to authenticate to the network. So the web key is the key if you're running web that you're using to encrypt your data. In this case, it's also the key you're using to authenticate to the network. Now, once a client has authenticated, the client tries to associate with the access point. This association only takes 4 frames and results in the client being associated with a BSS, basic service set, or an access point in infrastructure mode. Another thing you should understand is the 802.11 state machine. There's 3 states to the 802.11 state machine. Basically, it's unauthenticated and unassociated, so that's how you start out. You connect your client to the access or to the wireless network, and at that point you're unauthenticated and you're unassociated. Next, you authenticate. If it's an open authentication, then you didn't have to provide anything. If it's shared key, you had to provide something. You're authenticated and unassociated. Then finally, you become authenticated and associated. So that's the last state in the 3 states of the 802.11 state machine. Next, let's talk about power management. Okay, power management. Now the IEEE specifies 2 power management modes a client can use. Active mode, which is always awake, also known as continuous aware mode or CAM, and power saving mode, which is known as power save polling or PSP. So in PSP, the station tells the access point that it's in a power save mode. The access point keeps track of this, and the access point buffers frames for the stations that are sleeping until they awake and request the frame. In the periodic beacon from the access point that it sends out every so often to all the clients on the wireless network, there is a TIM or a traffic indication map. Now this TIM tells the stations what stations have traffic buffered and are waiting for the access point to be delivered. So if the station has traffic, it will awake and it will request its traffic from the access point. So if you're using active mode or always awake or continuous aware mode, that's probably what, maybe your PC's doing. It's always connected. It's just sitting there. It's always on the wireless network. Now, on a laptop, usually devices that are trying to save on battery, that's typically devices that are using power save polling, PSP, or power save mode. And so they're sleeping. They're trying to conserve their battery. Periodically, the access point sends out a beacon, says whether or not it has traffic to be delivered or not. And if there's traffic to be delivered, the station sees that, wakes up, and then requests its traffic. So that's what power management does, and that's how it works on a wireless network. In summary, I hope you've learned a lot about wireless terminology, radio frequency math, all the different things that go along with that, like decibels, dBi, dBm, dBd, watts, volts, amps, milliwatts, how to calculate everything, spread spectrum technology, signaling of wireless LANs, all the alphabet soup that goes along with 802.11 and its various standards, different types of wireless networks, authentication and association of wireless networks, and how power management works on wireless networks. So stay tuned for designing and deploying wireless networks in our next video. Thank you.